Chapter 13 focused on computing derivatives of multivariable functions, and in Chapter 14, we're going to focus on computing integrals of multivariable functions. 14.1 is just a quick introduction here to double integrals as we work our way up to higher dimensional integrals. So first, let's define what a double integral is. If f is a function of two variables that's continuous and non-negative on a region R in the xy plane, then the volume of the solid enclosed between the surface z equals f of xy, and the region R is defined by the double integral over the region R of your multivariable function f of xy dA. And this is called the double integral of f of xy over R. So this is just an analog of what we learned in Calc 1, where the single integral is the area beneath the curve. So you might recall that if we sketch a function in the xy plane and we pick some values a and b on the x-axis, this region that I have shaded here, that area is denoted as the integral from a to b of f of x dx. All right, and so we're just going up a dimension. When I add a dimension to area, it becomes a volume. So you'll notice now we have two variables, two integral signs, two variables in our function, and instead of a dx or a dy, we have a dA. So we'd like to better understand what that differential dA is actually representing. All right, so first let's kind of break down the symbols. We have that these two symbols, both this integral and this integral, are partial definite integrals. All right, definite in the sense that we have limits of integration, either a to b or c to d, and partial because this is a function of two variables on the inside, but we're only integrating with respect to one variable. So very similar to partial derivatives where we have multiple variables happening, but we're only taking the derivative with respect to one variable. Now we're going to talk about taking the integral with respect to one variable. All right, so we have that the first integral is the partial integral with respect to x, and in that case, we're going to hold y fixed, and we're going to integrate with respect to x. And then similarly, we have the second integral, which is the partial integral with respect to y, where x is being held fixed. Now we can work with these together, and we have what's called iterated integrals right here in this definition. And so how you interpret these is you read from the inside out. You'll notice that I've just grouped this inner term together. This means that you're integrating with respect to x first, using your fundamental theorem of calculus to evaluate your antiderivative from a to b, and then you're going to reintegrate that answer that you got from the first integral, but then with respect to y. And then likewise in the other case here, where you're going to integrate with respect to y first, and then second with respect to x. So these differentials are so important. A lot of times in Calc 1 and Calc 2, I see students just leave off the differential. They don't write a dx and they don't write a dy. And you can get by with doing that in Calc 1 or Calc 2 because it's understood what variable you're working with because there's only one variable involved. If you leave off your differentials now in Calc 3, I have no idea what integral you're taking with respect to. So make sure you include your dy dx or your dx dy to indicate which variable you're going to integrate with respect to first. All right, so let's just jump right into our first integral. Throughout this chapter, we're still assuming all of the techniques of integration that you learned from Calculus 2. So U substitution, integration by parts, trig substitution, all that good stuff is still going to hold in these higher integrals as well. So let's look at number 4. The first thing you want to do is identify what you're integrating with respect to. So for this first integral, again, if you want, you can put parentheses here to really call out what you're working on. I want to integrate with respect to dx. So I'm going to start by writing my first integral from -2 to 0. We'll deal with that in a moment. And now inside the brackets, I'm going to carry out the integration inside. So first I'm going to integrate x squared. That's going to be a 1/3 x cubed. And now the next term, you'll notice that there are no x's there. So that y squared is just considered a constant. So how do you integrate a constant? Well, you just tack the variable that you're working with on top. So this becomes an xy squared. All right, now I want to evaluate this expression from -1 to 2. But what variable am I evaluating? So oftentimes I'll indicate that by saying, well, I'm going to plug this in for x. And I know that I'm going to use the x variable because I just integrated with respect to x. All right, and then don't forget your differential here out on the end. This differential here corresponds to this integral out front. All right, so now let's go ahead and apply the fundamental theorem of calculus. I'm going to rewrite my initial integral. Next, I'm going to evaluate at 2. So I have 8/3 plus 2y squared. And now I'm going to subtract evaluating at -1. So I have a -1/3 minus y squared. And again, being careful to include that differential at the end. You can immediately start integrating with respect to y. However, I recommend first you simplifying inside the brackets so that rather than integrating 4 terms, you can just integrate 2 terms. So I'm going to recopy the integral, and instead I'm just going to combine inside. So I have 8/3 minus a -1/3 becomes plus, so 9/3 is 3. Again, distribute that negative to the y squared. I have 2y squared plus y squared is a 3y squared. All right, at this stage in the game, we're down to a Calc 1 integral. I don't need any techniques of integration. I can just integrate directly. I get 3y plus y cubed from -2 to 0. Again, if you want to indicate that you're plugging in for the y variable, you can. In this instance, it's understood because there's only one variable being involved. So we get 0 when we plug in 0. And we get -6 minus 8 when we plug in -2. And so our final answer here is a +14. Again, geometrically, the interpretation is if we consider the surface z equals x squared plus y squared, which we should recognize as a paraboloid, we're finding the volume beneath the paraboloid x squared plus y squared that lies over the rectangular region where y is ranging from 0 to -2 and x is ranging from -1 to +2. So there's a little rectangle in the xy plane. We're finding the volume beneath the paraboloid over that rectangle. All right, let's take a look at our next example. We're sneaking in some trig functions here. We want to calculate this double integral. All right, so for this one, we want to start by integrating with respect to y. You'll notice here that y is stuck on the inside of the cosine function, and we have something more than just a y inside the cosine. So we need to utilize u substitution here. I'm going to substitute for that entire inside, u equals xy. So now what I want to find is, I would like to find dy, all right? That's my goal. So let's start by finding du dy. So I want to take the derivative of u with respect to y, which is x. So in other words, we say that dy is 1 over x du. So let's go ahead and plug that in. I have my first integral out front. And then I would like to integrate my inside. For now, I'm going to leave off my limits of integration since I'm switching to u. And I have my x times cosine of u. And then my dy is a 1 over x du. So you'll notice that I have this nice cancellation here. Those x's cancel. And I can now integrate the cosine function with respect to u. The integral of cosine is sine. So rewriting my first integral, and then I got out a sine u, but I'm just going to go ahead and plug in for u. So this is a sine of xy. And then my limits of integration were with respect to y. So I want to evaluate y from 1 to 2. And then at the very end, I want to integrate with respect to x. And I did forget that dx over here. So I'm going to sneak that in at the end. All right, so let's go ahead and apply the fundamental theorem of calculus. I have my first integral. Then I have sine of 2x minus sine of x dx. All right, now at this point you can decide if you want to go through and show a u substitution for this 2x. By all means, you are welcome to do that. If you feel comfortable recognizing that that u substitution would kick a 1/2 out front, I'm perfectly fine with you skipping that step as well. So do whatever you feel comfortable with. I'm going to skip it, and I'm just going to integrate this directly. This is going to give me a negative 1/2 cosine of 2x. And then my double negative turns into a plus cosine of x, where I'm evaluating x from pi over 2 up to pi. All right, so let's plug it in. I have a negative 1/2 cosine of 2 pi plus cosine of pi minus a negative 1/2 cosine of pi plus cosine of pi halves. All right, so one of these terms vanishes. Cosine of pi halves is 0, so that's gone. And then the other terms remain. All right, so cosine of 2 pi is 1, so I have a negative 1/2. Cosine of pi is negative 1. And then I have this double negative becomes a plus. 1/2 cosine of pi is a negative 1. So lots of bookkeeping here with the negatives, but in the end, we get a value of negative 2. And again, keep in mind what this is representing. It's representing the volume beneath the surface defined by x cosine of xy over this rectangular region defined by the limits of integration. All right. So to start the top of page 2, we introduce what's known as Fubinis Theorem, and it says the following. If you have a rectangular region, and we'll define that as x is ranging from a to b and y is ranging from c to d, and if you know that your multivariable function f of xy is continuous on this rectangle, then the order of integration doesn't matter. So what you'll notice is, first of all, we're finally fleshing out what this dA notation means. dA is representing the differential with respect to the area. Now, since we're working with rectangles, we know that the area of a rectangle is the base times height, right? And so we have the x direction times the y direction, and Fubini says is the same as the y direction times the x direction. Now, if you flip-flop the order of integration, you must flip-flop the limits of integration as well. So you'll notice that from this double integral to the third double integral, those limits of integration have been switched as well. So make sure that you have those in the correct order. All right, so let's look at 14. Evaluate the double integral over the rectangular region R. And so we have our rectangular region. It's just the unit square there in the xy plane. So x is going from 0 to 1, y from 0 to 1. Fubini's theorem tells us that since we're integrating over a rectangular region, the order in which we carry out the integration doesn't matter. So you get to choose. Do you want to do dy dx or do you want to do dx dy? It's your choice. Sometimes one choice is better than the others depending on the integrand. Now when I look at the integrand on 14, it's really a wash. There's an x and a y on top, and the bottom is also symmetric in x and y. So it truly, truly, truly does not matter the order in which you set this up. So just pick it. I'm going to choose dx dy just to keep it in alphabetical order, no other reason than that. And furthermore, both of these limits of integration are the same, so we don't have to worry about that. Let me rewrite my integrand. And now I'm going to replace my dA with a dx dy. Okay, so now I want to carry out the integration. First, I'm going to focus on integrating with respect to x. And this integrand is a little bit more complicated where I'm seeing x's on the numerator and the denominator. So I can't just integrate directly. So I need to ask myself what technique of integration is most appropriate here. When in doubt, you should always try u substitution. And the first thing that comes to mind in this problem of what to choose for u is whatever is the innermost function. In this case, it's going to be what's underneath the square root. So let's let u be x squared plus y squared plus 1. And I want to find the derivative of u with respect to x. And I know that I want to choose x because my differential that I'm working with is a dx. So I want to have that involved. So this derivative is a 2x. You'll notice that the y squared and the 1 both go to 0 because I'm taking this partial derivative and those are constants. And so this tells me that dx, if I solve for it algebraically, is du over 2x. So let's go ahead and make this substitution. Again, I'm going to write question marks here because I'm now switching into the world of u and I'm leaving x's behind, and so I don't want to use my x limits of integration. On top, I have xy. On bottom, I swap that for a square root of u, and then I just found that dx is du over 2x. And then again, remembering that dy there. Now I'm going to cancel out all of my x's. And at this point, I know that this was a successful u substitution because I was able to get rid of all of my x's and leave everything in terms of u and y. Let me just do one more step here, and I'm going to rewrite this. I'm going to pull this coefficient of a 1/2 out front because I can. And then I'm going to rewrite my square root as a y u to the negative 1/2 du dy. Now, if you wanted to, this is optional, you could take this y, and since it's technically constant in the eyes of the integral with respect to u, you could stick it here in between the two integrals. You can't pull it all the way out front because it's not a constant with respect to the integral in terms of y, but in this case, it is a constant in terms of the inner integral. So that is an option that you have. Now let's go ahead and integrate this power function. So I have my 1/2 integral from 0 to 1. My constant y is still coming along. And then I get a u to the 1/2 divided by 1/2. And I want to evaluate from something to something, right? We didn't change it in terms of u. And then finally, I'll want to integrate with respect to y. So let's do a couple of things here. First of all, let's flip this division by 1/2. It becomes multiplication by 2. And so what we see is that's going to cancel with this 1/2 in front. And then furthermore, let me trade my u to the 1/2 back for what my original u substitution was. So recopying my integral, recopying my y, this becomes a square root of x squared plus y squared plus 1. And I want to now evaluate where x is running from 0 to 1, dy. Okay, so now let's go ahead and apply the fundamental theorem of calculus. So I'm going to do a parentheses here. First, letting x be 1 reduces this to y squared plus 2. And if x equals 0, I get y squared plus 1. All right. So where we're at now is I have technically 2 integrals to compute. So let me actually distribute the integral and the y here to both places. I have the integral from 0 to 1 of y square root of y squared plus 2 dy. Take away the integral from 0 to 1 of y square root of y squared plus 1 dy. All right, so in both of these cases, we need a u substitution. So to keep them straight, I'm going to call the first one u sub 1, and that's going to represent y squared plus 2. And I'm going to let the second one be u sub 2, which is y squared plus 1. Their derivatives happen to be the same, right? du1 is going to be a 2y dy, and du2 is going to be a 2y dy. And so in both cases, I can solve for the differential dy, and I get du1 over 2y, and dy equals du2 over 2y. All right, so now let's go ahead and plug these things in. Just to keep you guys on your toes, what I think I'll do is I'm going to change my limits of integration in both cases. So to do that, in case you forgot, all you want to do is take those limits of integration and plug it into your u function in each case. So let's take a look at the first integral. I want to take 0, and I'm going to plug it in for y, and that means that u1 becomes 0 squared plus 2, which is 2. And now take 1, plug it in for y, and u1 becomes 1 squared plus 2, which is 3. All right, so now I'm not going to resubstitute in the end. I'm just going to evaluate in terms of u, and I have y times the square root of u1, and dy became du1 over 2y. So we see some cancellation here. And then you can also pull your 1/2 out in front and rewrite your radical, whoops, as a 1/2 power. All right, and then let's also come back to our other integral up here. So very similar, I'm going to plug 0 in for y. u2 becomes 0 squared plus 1, which is 1, and plug in 1 as well. So u2 becomes 1 squared plus 1 is 2, and now I have a y square root of u2, and this is times du2 over 2y. So again, just as in the previous integral, our y's cancel. We can factor that 1/2 out front, and we can rewrite our radical as a 1/2 exponent. All right, so now we're in good shape. We can just integrate directly. And I'm going to run out of room, so I'm going to have to write on the margin here. So we have 1/2. And then when I integrate, this is going to become, I add 1 to the exponent, 3/2 multiplied by the reciprocal, 2/3 u1 to the 3/2 power. And this is where u1 is ranging from 2 to 3, minus 1/2. Same thing here, 2/3 u2 to the 3/2 power. And this is ranging from 1 to 2. All right, the only one that we can really fully evaluate is when I plug in 1 for u2. Otherwise, I'm going to leave these other things just as 3 to the 3/2 power or 2 to the 2/2 power. But before I do that, I'll go ahead and just simplify my coefficients by knocking out those 2's. All right, so where we're at is a 1/3, 3 to the 3/2 power minus 2 to the 3/2 power. And then moving on to the other set, I have a 1/3, 2 to the 3/2 power minus 1 to the 3/2 power is just 1. All right, and so lastly, if you want, you can combine. I can factor a 1/3 out completely. And remember, this negative goes through. I end up having 2 of the 2 to the 3/2 power, right? So I'll just write this as, I have my 3 to the 3/2 minus 2 of the 2 to the 3/2, and then plus 1 when I distribute that negative. Now, certainly you could simplify this since these have like bases. So that's up to you. If you wanted to go one step further, this is an understood 2 to the first power. So you could write this as 1/3 3 to the 3/2 power minus 2 to the 5/2 power plus 1. So this is as simplified as we could go. But on a quiz or a test situation, I would give you full credit at this point because you have fully computed the integral and you have evaluated at your limits of integration. So that is an appropriate answer. All right, so we have one more example here, number 30. I want to find the indicated volume. So I want to find the volume under the surface, z equals 3x cubed plus 3x squared y, over the rectangle where x is ranging from 1 to 3 and y is ranging from 0 to 2. All right, so this is going back to that original definition at the top of page 1, which says that the geometric interpretation of the double integral is that it finds the volume under the surface over the region that you're integrating over. So we know that the surface we're integrating is 3x cubed plus 3x squared y. So that surface serves as your integrand. Now we need to decide, do we want to integrate with respect to x or with respect to y first? Fubinis theorem tells us that we can choose whichever way we want. So this is truly up to you as to whether you want to do a dx dy or a dy dx. I personally don't think it's going to make much difference. So I'm going to choose dx dy. Now the order in which I choose those, the sequence of integration then dictates where my limits of integration go. So since I chose to integrate with respect to x first, my inner limits of integration need to belong to x. So I'm going to put those in as the integral from 1 to 3, and then my outer integral is y, so I'm going to run from 0 to 2. All right, so first let's go ahead and integrate with respect to x. I'm going to copy my outer integral, and now I'm going to integrate with respect to x. That gives me a 3/4 x to the 4th. Now when I add 1 to the power, that becomes cube, and divide by 3 is just going to cancel out. So I get an x cubed y. And I want to evaluate all of this where x is ranging from 1 to 3. And then of course a dy in the back. All right, so let's go ahead and plug in 3 and 1 for our x values. So beginning with 3, I have 3/4 of 3 to the 4th. That's the same as 9 squared, which is 81. Minus 3 cubed y, so that's 27y. And then take away, evaluating at 1. 3/4 plus y. Okay, so let's go ahead and combine what we can. Whoops, and I just noticed here, let's make this quick correction. That minus should be a plus. All right. Okay, so I have 81 times 3 is 243. Minus 3 is going to be 240. So I have 240 over 4, which I'll simplify that here in a moment. And then I have a positive 27 minus y gives me a positive 26y. All right, so 240 over 4 is going to give me 60. All right, and now I'm smooth sailing from here because I'm just integrating a polynomial. So I get 60y plus 13y squared running from 0 to 2. And so that is 120 plus 4 times 13, which is 52, minus 0 plus 0. And so in the end, I get a volume of 172 cubic units. All right. So we want to end this section by discussing some properties of double integrals. These are all very similar to the properties that we discuss of single integrals, so none of these should be surprising. The first is that constants in front can be pulled in front of the integrals. So we see it right there. This is again assuming that C is a constant. Double integrals can distribute across sums and differences. And furthermore, if you can split up your region to two individual regions or subdivide it, then you can split up your integral over those two regions as a sum. So this is very similar to when we have an integral from A to B. We can write it as the integral from A to C plus the integral from C to B. Same idea here, except for we're talking about a two-dimensional region rather than a one-dimensional interval here. All right, so we can use these properties throughout when we're computing multiple integrals. That's it for section 14.1.